Hello, everyone. I hope you guys are doing all right. So let's get started. Let me share with you my PowerPoint slides. Okay, so we'll be looking at section 16.7 today on relative motion analysis. So this time we'll be looking at how to actually solve for the oscillation. Okay. Yeah, objectives here. So you should be able to resolve the oscillation of a point on a body into components of translation and rotation. Okay, so basically that means you should be break the oscillation in the translational component and also rotational component. Okay, we'll talk about in details that, and then you should be able to determine the oscillation. Okay, by using this relative motion analysis. We'll be doing quiz, lecturing, and then attention and concept quizzes, and then a couple examples. At the end, if we have time, we can do a group problem solving. Okay, so that's the plan. As usual, we'll start with reading quizzes here. All right, so go ahead and then send me your answers in the private chat. Okay. All right, I think I got all your responses. So the first one says, if two bodies contact one another without slipping, and the points in contact move along different paths, the tangential component of oscillation will be, so the tangential component of oscillation of the two should be the same, okay? So the same, and the normal components of oscillation will be, that will be different because normal component will be either V squared over R or omega squared over times R. So the R will be different, okay, in many cases. All right, so then on this one, it should be B. Well, this first one is B. The second one here, it says, when considering a point on a rigid body in general plane motion, concerning its total oscillation, so this one should have both absolute oscillation and relative oscillation components, okay? It should be A here, okay? And then we'll talk about that later because usually we'll pick a point as a reference point. So the oscillation is equal to the absolute oscillation from that point plus the relative oscillation with respect to that point, okay? So those two components. All right, so this guy is A, so 1 is B, 2 is A, all right? Okay, so let's take a look here. All right. So previously, when we say for the relative motion analysis, we actually did this for velocity. So we had like VB plus VA equals to let me see. Let me put this on here. So let me write this on the paper here. You can see. So previously, when we had this, we had like VB equals to a base point, the velocity of that one plus, okay, and then VB with respect to A. So that's what we had earlier. So if we are looking for oscillation, then we are going to do time derivative of the equation, okay, on the right hand side and then on the left hand side. So on the right hand side, if you do time derivative of this guy, that gives you the oscillation of B, point B. All right, that should be equal to oscillation of point A plus this relative oscillation of point B with respect to A. Okay, so that's this equation on this slide shows here. All right, so if you do time derivative of that, gives you time derivative of this guy plus this guy. Okay, so then on this one, this is the absolute oscillation for point B. This is the absolute oscillation for point A. Okay, so then the two should equal A sub B should be equal to A sub A plus A sub B relative to A. Okay, this is the relative. Okay, now keep in mind when we talk about the velocity relative motion analysis, this guy is due to rotational motion of the body. Okay. So then if there's rotational motion of the body, then the oscillation in this part will have a tangential and normal components, okay? So in addition to the absolute oscillation for this guy, there's a tangential and normal component, okay? So you'll have actually, basically you'll have 3 terms for oscillation of B, okay? So this is the result, okay? So then A sub B is going to be equal to A sub A plus the tangential component of this guy and then the normal component of that guy. Okay, so 3 terms here. All right, this is the absolute oscillation of point A. This is due to the rotational motion, and then this is relative to point A. Okay. All right. You can also look at geographically or graphically. So point A will be the base point, okay, if it goes in that direction. And then point B will be rotating with respect to point A, okay, alpha with alpha, and then with omega, okay, so you could have both of them. So then this is equal to that guy, A sub B is equal to A sub A plus the tangential and normal component, okay, so you can see from the figure here clearly that this is the normal direction, this is tangential direction, okay, the components. All right. Now, earlier in the chapter, we say for the if a body is having rotational motion, then the tangential component will be of the oscillation will be alpha cross R B with respect to A. Okay, so you want to refer this to the first lecture of this chapter. Okay, so that gives you this tangential component of it. Okay, and then for normal component, it's going to be minus omega square R B sub A. Okay, so this is, you can also refer to the beginning of the chapter for this component. Okay, so then there's two components. So then the oscillation equation would becomes A sub B equals to A sub A plus, okay, this is the tangential direction oscillation. This is the normal direction oscillation. Okay, all right. So, and then the last term was coming from like omega cross, if you remember, this is like plus omega cross R, okay? So you guys have did this in the homework. By the way, homework solution is posted online, okay? So you can go check with the solution and then let me know if you have any questions about the solution, okay? Most of you guys are doing all right, okay? So just in case if you have questions, you can reach to me, okay? Either send an email or you can do the office hour view via Zoom, okay? So I post the link on Moodle, you can click on that and then I'll get connected to you with you on Zoom, okay? All right. So the procedures you take for relative motion analysis for solving for oscillation. So here are the procedures. And the first one, again, you need a coordinate system, okay? Say set up X and Y and Z, okay? And then you can draw the connected diagram of the body. So draw like which part is its motion, and then if there are known quantities, you want to indicate them as well, all right? And then so for oscillation of A, okay, if it has tangential and normal direction, you want to indicate them. So sometimes this guy, it's not just purely translational motion or translational oscillation. It could also have like tangential and normal direction of oscillation, okay? And then for B, it could also have that, okay? But if you are applying relative oscillation equation, then this is what you have, okay? So AB is equal to A sub A plus alpha cross RBA minus omega square R. Okay, so these are vector equations. Okay? So you probably realize that in the couple of sections ago when we talk about relative motion analysis for velocity, so the usefulness of using the vector equation is you can set up the equation so then the I component on the left-hand side will be equal to the I component on the right-hand side, and then J component from the right-hand side should be equal to J component on the right, okay? So in that way, you can set up two equations. So by looking at the components, okay, the X and Y components. So starting from one equation, you can actually could have two unknowns, all right? And then later on, you can break the vector equation into the X and Y components so you can solve for the two unknowns, okay? All right. So we'll take a look at a couple of examples, starting with example one here. All right, so this one says if you are given a rod A and B, now for point A, its oscillation and velocities are given. Its oscillation and velocity are given. So it's asking you to find the oscillation of the rod, and then yeah, the angular oscillation and the oscillation of the rod at point B, okay? Angular oscillation of the rod and then the oscillation, all right? So in this case, we can follow the procedures listed in the previous slide, okay? So first we can set up an XY coordinate system. We can take X to the right, Y upward, okay? Then naturally Z is coming out of the ball, okay? So that's what we should have for the XYZ coordinates. And then let's see. So by given that the velocity at this point A and oscillation at this point A is known, so we can see that A is going straight downward, B should be going to the right, okay? So we know the direction of the velocity of B and A. So then we can actually draw the instantaneous center, okay, of zero velocity, okay? So then IC can be determined. If we can determine IC, we can actually calculate the omega, okay? So then according to our geometry here, so this guy, if this is 4, this is 5, then this side or this side should be 3, okay, because this is the right angle, okay. So then if this is 3, then distance from the instantaneous center of 0 velocity to point A should be 3, okay. Given VA is 6, then omega can be determined by doing VA divided by R, okay. So 6 divided by 3, that gives you 2, all right. So we can determine the angular acceleration quite easily here by using the instantaneous center of 0 velocity, okay. Now, next we'll be determining the acceleration of point B, okay. So we can write acceleration of point B, AB to be in this direction, okay. We can assume that's the case, okay. And then at the end, if it turns out that that's going to be negative, that means the original assumption was not right. So then it's going to be in that direction, okay. So it's safe to just set up like this, but we can determine if that's right or not later, okay. So A sub B is to the right. So that means A sub B is going to be having the positive I component, okay? So we can write this in this fashion. A sub A is going downward, so it's negative J, negative 5 in J direction. A sub B should be equal to a numerical value times I, okay? In I direction, positive I direction. And then according to the relative acceleration equation, A sub B should be equal to A sub A plus alpha cross R B sub A, okay, minus omega square R B sub A, okay. So again here, so because alpha, you can, or the, yeah, let's see, the omega here, you can, omega, I think it's quite straightforward. It's going to be in this direction, all right. Now you can assume alpha is going to be in the same direction, all right. It doesn't matter if it turns out to be negative, then that just means it's going to be in the opposite direction at the end, okay. So if alpha is in this counterclockwise direction as indicated, then you can use your right hand rule. You can curve your 4 fingers in the direction that is counterclockwise, okay. So your thumb is pointing outward, out of the screen. So that means alpha vector should have a direction in the k direction, okay, in the out of the screen direction, that's the z direction, positive z direction. So in vector form, you should write it as alpha k, okay, cross product of r from b relative to a, okay, so from b relative to a, that means starting from a pointing to b, okay. So it's 3 in the I direction, it's negative 4 in the J direction. So 3I minus 4J, okay. Omega is 2 square, okay. And then 3I minus 4J, that's the R B with respect to A, okay. Then you can do the cross product here, distribute K into the I and then into the J component. So so it's minus 5J here, okay. Now if you do K cross I gives you J, positive J, okay. So 3 alpha J here, all right. K cross K or K cross J will give you negative I, but it's negative in front here. So negative becomes positive. So 4 alpha I, okay. And then you're going to distribute the square, 2 squares into the parentheses here. Okay, so minus 2 square gives you 4 times 3 gives you 12, minus 12i. And then minus becomes positive, okay? 4 times 2 square gives you 16, okay? Now putting all the j terms together and then the I terms together on the right, you got 4 alpha minus 12, okay? 4 alpha minus 12. For the I component, for the J component, you have 3 alpha, okay? And then minus 5 plus 16 gives you 11. All right, so this is the J component. On the left-hand side, you only have I component, okay? So that means the J component should be equal to 0. Then you can solve for your alpha, okay? And then once you solve your alpha, you can solve for your A sub B, okay? So that's what's going on here. So setting up those 2 equations, for the I and J components, okay, on the left, I component on the left then should be equal to I component on the right, J component on the left should be equal to J component on the right. Then solving for the two unknowns, you get oscillation of B, okay, indeed to be negative, okay, here. So it gives you negative sign. So that means our original assumption of direction for this guy wasn't right. So it's indeed as going in that direction, the oscillation, okay. The velocity is going in that way, the oscillation is going in the other way, okay. So just simply means it's decreasing in velocity, okay. Also for the alpha, it gives you alpha as negative. So then simply means, okay, our original assumption for direction of alpha wasn't right, so it's in the other direction. So it's actually the clockwise, okay, in that direction, okay. Any questions you guys might have? All right, so then let's move on. So another topic here in this section talks about when two bodies in contact. Okay, so when two in contact without slipping, okay, this is what happens. So if you have two gears rotating and then in contact, okay, at a certain point there. So a point A here from gear B should have different paths than a point A prime from gear C. Okay, but when they are in contact, then they will share the same tangential. Let me see. Yeah. So the tangential component of the oscillation will be the same, and then also tangential component of velocity should be the same. Okay, just keep that in mind. So in that case, then you'll have this equation. You can have the oscillation of a point in the tangential direction equals to the oscillation of a prime in the tangential direction. Okay, so that implies that alpha oscillation of B gear times radius of B is equal to oscillation of C gears times radius of C. Here, oscillation refers to angular oscillation because it's alpha. Okay. All right. But the normal direction oscillation should not be the same because here normal direction should be omega squared times r, and then here should be rc, here should be rb. So they are different radius, okay, for most of the time. All right, so let's do an attention quiz here. Actually, two of them. I'm going to set up breakout rooms so for you guys you can have discussion on the breakout rooms. Okay. So we'll have 4 rooms. Okay, automatically generated. Yeah, so join the breakout rooms and then work on this too. I think we can close the room in about say 3 to 5 minutes. Okay, go ahead and then do that. All right, so I have asked you guys to come back to the main section here, and then you guys are submitting the responses here. I can see all the responses. So yeah, looks like everyone has agreement on this. B on the first one and then A on the second. Okay, so you're actually right. Okay, so on the first one, if they're in contact, okay, so then they should have the same oscillation at the contact point. Okay, so the first one will be B, all right, and then the second one here, it's asking you the tangential component of the thing A is if it's 100, okay, on B, determine the angular oscillation of it. Okay, so angular oscillation, so the first one here, it's B, and then the second one should be, all right, should be A. Let me just put this out, okay. But for oscillation, you're doing tangential oscillation should be equal to angular oscillation times R, okay. So in this case, it tells you 100 feet per second square to be the tangential. The alpha is what you're looking for, but it gives you R is 2, okay, so alpha times 2. So then alpha will be 50, okay, so 50 radians per second, okay, so that's A, okay, so everyone got that right. Let's move on here. So another content here in this section talks about rolling motion, okay? So if you have rolling motion, especially when say the disk here is not slipping, okay? So then at this point, A point, you will have oscillation be 0, okay? So then you can actually use that one, okay, as your instantaneous center of 0 oscillation, okay? So, but when you have rolling motion here, so then alpha is the angular oscillation of the rolling motion, okay, with respect to the G point here, and then omega is that. So, so then you can look at here. So if you are looking at the contact point over here, okay, so assuming that looking at the moment of the contact just before the contact and then just right after the contact, okay, so I can imagine that if this guy rolls down here, so before A is touching the ground, A should have just a velocity that is going downward, okay? And then after it just leaves the ground, it should have the velocity going upward, okay? So at that point, you can see that for point A, the oscillation, although at point A, its velocity is 0, but it should have a non-zero oscillation, which is pointing upward, okay? So in that direction, okay? So that's A for A, okay? All right, and then it probably have, let me see what the text says here. So yeah, G would be moving in the line here, so then oscillation of G would be in the horizontal direction, okay? So if alpha and omega are known, then you can apply relative velocity and oscillation equations to point A. So both of the equations you can apply, okay? All right, so yeah, you can treat point A as instantaneous center of 0 velocity, okay? But the velocity is not 0, okay? So we'll just check on the velocity. It shouldn't be 0, okay? Because the next moment it wouldn't be 0, so that means the oscillation is not 0. Okay, so point A has 0 velocity, okay? So then you can set up the velocity relative motion, or the, let me see, what's this? So relative motion equation for velocity, okay? So this is the one you can have, okay? And then you can put the in vector form, so then you'll be doing the again the I component and J component. So omega, if this is going clockwise, then the omega is use right hand rule. So omega, the direction, vector direction is going into the screen, okay? So minus omega k, okay? Cross J, cross Rj. So in that case, you can determine your Vg is going to be omega times R, all right? And then that's in the I direction, okay? Now for the oscillation, okay? So yeah, as I said, just before it touches the ground, its velocity is directed downward, and then just after it touches the ground, it's upward. So then oscillation is upward, okay? All right, so if you are looking for oscillation at point G with respect to the point A here, then you are setting up the oscillation equation, relative oscillation equation, okay, like this one. And then at point A, it's just in the J direction. Now point G, it should be in just in the I direction because the center goes just along the straight line, okay, to the right, excuse me. And then plus alpha in vector form. So again, this is minus alpha because alpha is going clockwise direction, okay? Cross J minus omega squared times Rj, all right? And then you'll be looking at the I component and J component of the left-hand side and right-hand side, okay? So K cross J will give you minus I, all right? So then minus minus becomes positive, okay? So Ag in the I direction, then will be just alpha times R, okay? That's what you have. And then AI, here, J component minus this J component, that should go to 0. So that means A sub I is equal to omega squared times R, okay? So you can determine both A sub G and then A sub A, all right? And then if you indicate the directions, this will be the direction, okay? A sub G should be just in the X direction, A sub A should be just in the J direction, all right? So that's rolling without slipping, okay? All right, now let's look at the concept quiz here. So you'll be referring to the equations in the previous slides from this one, right? Okay, let me, so just the breakout room is still there. Let me just reopen the breakout rooms. You guys can work on them together, okay? All right, so you guys all says B and A, okay? So, and then again, you are right on this one, on this two, okay? So, the oscillation, relative oscillation of point A with respect to G, so that means you are doing A minus A sub G, okay? I can start from the original expression. Let me pull up my little screen here. Let's see. Okay, got it. All right, so this is equal to, if you choose G to be the base point, then plus, okay, alpha cross RB with respect to G minus omega square RHA with respect to G with respect to G. Okay, so then we are looking at this two terms, okay? And then in the previous slide, we have shown that the first term will be equal to, so in this case, it's going to be minus, okay? Minus R alpha times R in the I direction, and then this guy will be the positive omega square times R in the J direction, okay? So that's for those two terms, okay? So then it's B, okay? Okay, so let me see. All right. So on the second one here, all right, on the second one here, you're looking for point B, the oscillation of point B. So with respect to G, all right, so again, then you're doing like A sub B minus A sub G. Okay, similarly, so you want to treat this similarly, like alpha cross R B with respect to G and minus omega square R B with respect to G, okay? So this time B is to the right, so then this guy is R times I, okay, for the R vector B sub G. Okay. Now alpha, because it's clockwise, so then it's minus alpha in the K direction, okay? So that cross this guy, minus omega square of R in the I direction, okay? So then K cross I gives J, but less minus, so alpha minus alpha I in the J direction, okay? Minus omega square R in the I direction, okay? That should be your A of B with respect to G, or this guy, okay? So the two components there, they should be both negative, okay? So that's option A there, okay? So you guys got these two right. All right. Any questions you guys might have before we move on? Okay, so let's move on here. On example number 2, so this one says the gear with a center at O rolls on a fixed rack. Okay, so it's looking for the oscillation at point A on the top. Okay, so that means at the bottom B here, the velocity is 0, but oscillation of gear is not 0. Okay, so we can take a look on this one together. So again, we'll be following the solution procedures. So first, of course you want to set up the x and y coordinate. Okay, so if not specified, then usually we take to the right to be positive, upward to be the y positive, to the right to be x positive. Okay, so so it says the gear rolls on the fixed rack without slip. Then A of the center O, okay, then it's also, it should be in the equal to AR. Okay, so we have seen this in the content slide like a couple of slides back. So that should be alpha times R. Okay, so then this oscillation of point A, point O can be determined. Okay, so if you go a couple of slides back at the center, okay, here, it's the G here. Okay, so A sub G is alpha times R. Okay, so then in the case in the example 2, the O is the center point. So then A sub O is alpha times R. Okay, to the right. Okay, so let's go here. All right, so alpha times I, 6 times 0.3. 0.3 is the radius, so 1.8 meters per second square. Okay, so this is A sub O. Okay, then once we have A sub O here, we can use the relative oscillation equation. We can figure out the oscillation at point A. Okay, so then this is what we are going to do. We are going to use this oscillation equation. Now the base point is O. Okay, our reference point is O. The interest point is A. Okay, so just changing notation here. Originally you have B and A, now you change it to A and O. Okay, so plus alpha cross R from A to O minus omega squared from R A to O. Okay, now alpha, all right, it's given as 6. It's the clockwise direction, so then means vector alpha should be in the minus k direction. Okay, so minus 6k. All right, and then A sub O is 1.8 okay, meters per second squared to the right. Okay, so this is that guy equals to minus 6k cross 0.3 J, because J is the R sub A with respect to O. So this guy is upward 0.3 positive. Okay, minus 12.3 J. All right, so then everything here is known here. So then A, oscillation of point A should be determined. Okay, so it's this guy here, 1.8 minus, actually, yeah, it's 1.8 here. Then this gives you I. Okay, K cross J gives you I. So then K cross J, let me see. Actually, K cross J gives you minus I. So J cross K is positive I. K cross J is minus I. Okay, so then 1.8 minus 1.8 times minus I becomes positive 1.8. So 1.8 I plus 1.8 I, 3.6 I. Okay, and the J component 12 squared multiplied by 0.3 is 43.2. Okay, so then that's the oscillation, okay, a point A, okay. And then I think you can, if you want, you can figure out. So this is expressed in the Cartesian coordinate, okay, or in XY components. You can, if you want, you can also calculate the magnitude by doing x squared plus y squared square root, okay, and then directional angle of tangent of y over x, okay, that gives you the angle, okay, if that's what you want. All right. So questions on this one?
Yeah, Dr. Ho.
Yes.
So there's no acceleration in the k direction then?
No, yeah, because this is the, yeah, this disk is rolling in just XY plane, okay? It's not going in the k direction. Yes, you are right.
Okay, cool.
All right. So let me see how much time do we have left. About 7 minutes. Okay, so then we'll just look at the group problem solving together, okay? So this one says, so A and B is rotating with angular velocity of 4 and then oscillation of 5 in the opposite direction. Okay, at this instance shown here. Find the velocity and oscillation of the slider block C. Okay, so looking for VC and then AC here. Okay, so let's take a look here. So by given omega of AB and then alpha of AB here, we can actually determine what's the velocity of point B at this instant. Okay, so that's something we can determine. It's just omega times r, and then this is in the negative y direction. Okay, so that could be determined easily. Put this small screen here, so when you guys check on this video later, you can also see what's going on in my little paper here. All right, so on the group problem solving, okay. So given the norms, we can determine the velocity at point B, all right, to be omega times r, and then that should be in the negative j direction, okay. So negative j, so alpha is 4 times 2, okay, the length of the rod, so that's minus j, so minus j, let me do it that way, so minus 8j, okay. This is V B, okay. And then oscillation of B can be determined as well, okay, because oscillation of B, this is just rotating with point A with respect to point A. So there will be a tangential component, all right, and then there will be a normal component because this is rotating, okay. We can see tangential component here, it's going into the positive, so alpha is going into the positive direction, okay. So then this is positive of alpha. This is the I direction, and then this is J direction. Let me just put the vector there, going that way. So this is the alpha I. It's in the positive direction. You can determine it by looking at the alpha direction of original alpha. Okay, and then plus the normal direction. Normal direction would be because this is rotating, so normal direction is going to be towards the center of rotation. Okay, so towards A, from B to A, so that's negative I direction. All right, so it's V squared over R or omega squared times R. Either way, that should be the same. So minus J. Okay, if you plug in the numbers, you'll get so for alpha is 5 times 2 in the I direction, and then minus V will be 8 squared over 2 in the J direction, okay? So that gives you 10 in the I direction minus 32 in the J direction, okay? So this is your oscillation at point B. This is your velocity at point B, okay? We need this to figure out the oscillation at point C, and then the velocity at point C, okay, by applying the relative oscillation and the velocity equation, okay? So let's see, let's look for the velocity first, okay? So because if you look at the slider C here, you can see it's going to just slide along the groove there, okay? So then it's going to be in that fixed direction, okay? So we are going to assume that this slider C here, it's going to be in that direction, velocity, and then also oscillation is in that direction, okay? It doesn't matter if we get negative numbers, that simply means we are, it should be in the opposite direction, okay? So then velocity in this direction, and then this is a like 3, 4, 5 triangle. So you can see that the velocity should have two components. In the x component, it should be the 4 over 5, okay? So 4 over 5 VC in the x direction, okay? So you can set up the velocity equation. V sub c should be equal to V sub a plus omega of BC rod cross R of C with respect to B, okay? So this is the velocity, relative motion velocity equation. So for this guy has two components. It's in that direction, so that means x is going to be negative, also y is going to be negative, okay, in the j direction. So this is left-hand side. VB is minus AJ, okay, plus, okay. So the omega here, all right. So let me see, do I have omega? Okay, so yeah, so in this case, you can see that, let me see. So we are going to assume this, yeah, we are just assuming this is in the counterclockwise direction, okay? So then we can write this way. So So then the vector direction should be in the k, positive k direction, okay? Cross R of CB, so it's point C with respect to B. So point C, let me see, is this given? Yeah, I think it's given. So it's minus 0.5 in the I direction, minus 2J. Okay, let's see. The figure here, my figure is being covered. Okay, yes. The geometry shows that X is 0.5, but it's to the left, so negative. And then the length, the Y direction is 2, okay? C is below B, so it's also negative, okay? So then you are setting this up. So in the equation here, you have this as one unknown, this as a second unknown, okay? You have two unknowns. You can do the algebra here. You can break them into X and Y component, okay? So I think we are running out of time, but I'll just let you know that's what you are going to do, okay? You are going to set X and Y, X or I from the left equal to I to the right, and then I from J from the right to equal to J on the right, okay? And you can solve for that. So omega BC will be equal to 3, and then VC will be equal to 2.5 meters per second, okay? So that's when you solve for this. Similarly, for oscillation, you are going to set up the oscillation of point C is equal to oscillation of point B plus, now you have three terms, okay? Alpha cross, okay, B with respect to C, or C with respect to B, sorry. And then minus omega square of R of C with respect to B, okay? I'll post the solution later, but that's the same thing here. And then you can set up, so you're looking at I component and J component, you have two unknowns, and then this is one unknown, this is two unknowns, okay? So you will solve for the two unknowns, okay? By that, okay? So similar procedure, okay? Questions you guys might have? All right, if not, then have a good weekend, guys. I'll see you back on Monday.
Bye, Doctor.
Bye. See you.
Bye, Dr. Ho.
Bye.